For most of human history, ignorance looked temporary. We stood beneath the night sky with almost no reliable knowledge of what those distant points of light were. They might have been holes in a celestial sphere, divine fires, or worlds beyond imagination. Each generation inherited mysteries that seemed permanent, only to watch many of them dissolve under better instruments and sharper mathematics. The pattern became so familiar that it quietly reshaped our expectations. Every unanswered question appeared to belong to the same category. We simply needed more time, larger telescopes, faster computers, or a more elegant theory. Progress itself became evidence that every mystery was eventually solvable. That confidence runs through modern science. We have measured the age of the observable universe to remarkable precision. We have traced the evolution of stars, mapped the large-scale distribution of galaxies, detected gravitational waves, and watched planets orbit distant suns. Problems once thought unreachable have steadily moved into the category of ordinary research. From that perspective, the future seems almost predictable. Humanity, or some civilization far beyond humanity, continues improving its tools until the remaining gaps disappear. Every equation becomes complete. Every hidden process becomes observable. Every unknown eventually becomes known. It is an appealing story. There is only one difficulty. Some of the strongest ideas in mathematics, computer science, and physics suggest that this picture may be fundamentally mistaken. Not because civilizations become extinct, not because technology stalls, not because the universe is too large, but because reality itself may contain questions that cannot be answered by any observer living inside it. This possibility does not begin with astronomy. It begins with an unexpected crisis inside mathematics. At the beginning of the 20th century, mathematics appeared to be approaching its own golden age. Many believed the discipline could be built upon a perfectly consistent foundation. Every true statement would eventually be proven from a finite collection of logical rules. Mathematics would become a complete machine for discovering truth. Then, in 1931, a young Austrian logician named Gödel demonstrated something few had considered possible. Within any sufficiently powerful formal mathematical system, there exist true statements that cannot be proven from the rules of that system. Even more striking, the system cannot establish its own consistency without stepping outside itself. The result did not imply that mathematics was broken. It implied that completeness has limits. No matter how carefully the rules are chosen, there will always remain statements that escape them. The horizon keeps moving. For decades, many regarded this as a profound result, confined largely to logic and mathematics. Physics seemed different. Nature is not a collection of abstract symbols. It is something we can observe, measure, and test. Yet, over time, another possibility emerged. What if physical systems themselves could perform computation? And if they can, what happens when the behavior of a physical system becomes equivalent to solving an undecidable computational problem? That question has become increasingly relevant in modern theoretical physics. Researchers studying quantum, information, many computational complexity, have identified classes of physical problems that inherit limits originally discovered in theoretical computer science. In some cases, asking whether a quantum system possesses a particular property can become mathematically equivalent to asking a question that no universal algorithm can always answer. iScience Direct. Notice what this does not mean. It does not mean physics has failed. It does not mean experiments become useless. It does not mean scientists should stop searching. Instead, it introduces a distinction that feels deeply unfamiliar. Some questions remain unanswered because we have not solved them yet. Other questions may remain unanswered because no method can exist that answers every instance of them. Those are completely different kinds of ignorance. The first disappears with better science. The second survives every improvement. Imagine building a computer powerful enough to simulate an entire galaxy atom by atom. Then imagine constructing a second machine thousands of years later that is 1 billion times faster. If the question belongs to the first category, eventually one of those machines succeeds. If the question belongs to the second, neither machine succeeds. Not because they lack power, because no amount of additional power changes the nature of the problem. This is one of the most uncomfortable shifts in modern scientific thinking. Progress no longer guarantees completeness. The universe may continue rewarding curiosity forever while still refusing to surrender every answer. Even the phrase, theory of everything, begins to sound less certain under this light. Physicists often use the term to describe a framework capable of unifying all fundamental interactions into a single mathematical description. That ambition remains one of the greatest goals in theoretical physics, but possessing a unified theory is not necessarily the same as possessing complete knowledge. Some physicists and philosophers have argued that even if such a theory exists, questions about its consequence may still encounter intrinsic computational or logical barriers. Others caution that Gödel's incompleteness theorems do not directly apply to empirical science in the same way they apply to formal mathematics. The debate itself reveals an important point. A final set of equations does not automatically imply that every meaningful prediction or explanation becomes accessible. A Springer. That distinction changes the goal entirely. Perhaps the greatest achievement of any civilization is not discovering every answer. Perhaps it is learning which questions belong to reality and which belong to the permanent edge where reality can no longer explain itself from within. Gödel showed that logical systems can contain truths they cannot prove. The next question is whether nature behaves like a logical system at all. At first, that comparison seems misplaced. Mathematics exists on paper. The universe does not. Galaxies do not consult axioms before they collide. Stars are not theorems. Black holes do not pause while an equation reaches a conclusion. Yet physics has gradually revealed something unexpected. The universe processes information. Every atom stores quantum states. Every interaction transforms information into new physical configurations. Even empty space carries measurable properties that influence what particles can do. Over the last half-century, information has shifted from being a convenient language for describing nature to becoming one of the central concepts in modern physics. Once that shift occurred, another possibility followed almost immediately. If physical systems process information, then physical systems may also inherit the limitations of information processing. The first hints appeared through an idea that had nothing to do with distant galaxies or quantum gravity. It came from a deceptively simple thought experiment introduced by Alan Turing. Imagine a machine that follows precise rules. It reads symbols, changes them according to a fixed procedure, and continues until it reaches a conclusion. Turing showed that such a machine could perform any computation that can be expressed algorithmically. More importantly, he also proved that there are questions no universal algorithm can always answer. His most famous example became known as the halting problem. Suppose someone hands you a computer program and asks a simple question. Will this program eventually stop running, or will it continue forever? For many individual programs, the answer is straightforward. You can inspect the code or simply let it run. But Turing demonstrated that no single algorithm can correctly determine the answer for every possible program. The limitation does not arise because existing computers are too slow. It does not disappear if processors become infinitely faster. It is woven into the structure of computation itself. That discovery transformed theoretical computer science. It also introduced a profound distinction that continues to shape modern research. Some limits are practical, others are fundamental. A practical limit can be overcome with larger telescopes, better detectors, faster computers, or more efficient mathematics. a fundamental limit remains untouched by every technological advance. This difference appears repeatedly throughout physics. Consider weather forecasting. Meteorologists have become remarkably successful at predicting atmospheric behavior over periods of days. Satellites monitor cloud systems continuously. Numerical models solve millions of equations every hour. Forecasts improve as measurements become more precise. Yet weather remains notoriously difficult to predict far into the future. Part of that difficulty comes from chaos. Tiny uncertainties grow over time until they dominate the outcome. Edward Lorenz discovered that systems governed by perfectly deterministic equations can still become effectively unpredictable because infinitesimal differences in initial conditions expand exponentially. The atmosphere is not random. It is sensitive. If no observer can measure every molecule with infinite precision, long-term prediction reaches a natural boundary. That lesson extends well beyond Earth's atmosphere. Planetary systems exhibit chaotic behavior over immense timescales. Orbital resonances accumulate. Small gravitational interactions amplify across millions or billions of years. Researchers can estimate broad statistical behavior. Yet certain detailed futures become increasingly uncertain, no matter how carefully the calculations begin. Determinism does not guarantee predictability. Those two ideas often travel together in everyday thinking, but physics separates them. The equations may be exact, while the future remains inaccessible. Quantum mechanics introduces an even deeper challenge. According to the standard interpretation, quantum theory does not merely hide information beneath practical uncertainty. Certain outcomes are described probabilistically until measurement occurs. Competing interpretations disagree about what this means physically, but they share an important consequence. Observation itself has limits. No experiment extracts unlimited information from a quantum system. The uncertainty principle is frequently misunderstood as a statement about imperfect instruments. It is not simply a technological obstacle. Within quantum mechanics, particular pairs of physical quantities cannot simultaneously possess arbitrarily precise, measurable values. Better equipment does not erase that relationship. The boundary belongs to the theory itself. These examples point toward a larger pattern. Again and again, science encounters situations where increased knowledge continues to produce extraordinary progress while revealing new categories of permanent constraint. The horizon retreats, but it never disappears. Some researchers now studies these constraints using computational complexity, a field concerned not only with whether problems can be solved, but how efficiently they can be solved. Two questions may both have solutions in principle, while differing so dramatically in required resources that one remains forever beyond any physically realizable civilization. The distinction matters. Suppose an answer exists, but would require more computational steps than there are particle interactions available before every star in the observable universe burns out. Has that answer truly become attainable? In a mathematical sense, perhaps. In a physical sense, perhaps not. Reality imposes budgets. Energy is finite. Time is finite. Memory is finite. No civilization escapes those constraints merely by becoming more advanced. The image of an infinitely capable future intelligence begins to weaken. Even a civilization, millions of years older than ours, must still compute using matter. It must still obey thermodynamics. It must still transmit signals below the speed of light. It must still store information in physical media vulnerable to entropy. Intelligence can become greater. It cannot become unphysical. That realization quietly reshapes one of humanity's oldest assumptions. Perhaps knowledge does not end where curiosity fails. Perhaps it ends where the universe itself refuses to supply enough information for the question being asked. If that possibility is real, then the greatest scientific discoveries ahead may not simply reveal what reality is. They may reveal with increasing precision what reality will never allow anyone to know. one assumption still survives. Even if some problems cannot be solved through logic or computation, perhaps they can simply be observed. After all, the universe has already done the calculation. The stars formed, the galaxies evolved. Black holes merged. If nature has already produced the answer, why not look directly at it? That confidence begins to weaken the moment we consider what it actually means to observe anything. No observer stands outside the universe. Every measurement must be made from somewhere. Every telescope occupies one location. Every signal requires time to travel. Every observation arrives after a delay that cannot be eliminated. Astronomy has always worked under this constraint. Looking farther into space means looking farther into the past because light has a finite speed. The moon appears about 1¼ seconds old. The sun is seen as it was roughly 8 minutes ago. The Andromeda galaxy reaches us after more than 2 million years. These delays are familiar enough that they rarely feel profound, yet they reveal something much larger. Observation is never simultaneous with reality. There is no universal now waiting to be photographed. Einstein's theory of relativity removed that possibility more than a century ago. Events that appear simultaneous for one observer may not be simultaneous for another, moving at a different velocity. Time itself depends on motion and gravity. The universe offers no privileged viewpoint. Every observer receives only a local version of reality. That limitation becomes even more severe when the expansion of the universe enters the picture. Galaxies are not merely spread across space. Space itself expands. For nearby galaxies, gravity can still overcome that expansion. But beyond sufficiently large distances, the stretching of space dominates. Light emitted today from certain remote regions will never reach us, regardless of how long we wait. Those regions have not disappeared. They remain physically real. They simply become permanently disconnected from our future observations. Cosmologists describe this boundary as the cosmic event horizon. Unlike the horizon you see standing on a beach, this one cannot be reached by traveling farther. It is created by the expansion history of space-time itself. Beyond it, information continues to exist. It simply stops being available. This distinction is easy to overlook. An inaccessible region is not the same as an empty region. The observable universe contains hundreds of billions of galaxies, yet it represents only the portion from which light has had enough time to reach us since the beginning of cosmic expansion. Current cosmological models indicate that the universe beyond this observable sphere may extend vastly farther, perhaps even indefinitely, though its overall extent remains unknown. If that picture is correct, then most of reality has never been observed by any human being. More importantly, much of it never can be. No larger telescope changes that. No more sensitive detector changes that. No civilization, regardless of its age, negotiates with the expansion of space-time. The limitation belongs to geometry itself. Black holes introduce an even sharper version of the same idea. For decades, black holes were treated mainly as places where gravity becomes overwhelming. Then, researchers recognized something even stranger. An event horizon is not merely a dangerous location, it is an information boundary. Crossing that boundary changes what can ever be known by distant observers. General relativity predicts that information carried across the horizon cannot simply return. Quantum mechanics, however, strongly resists the idea that information is truly destroyed. The resulting conflict became one of the deepest problems in theoretical physics, known as the black hole information paradox. Entire generations of physicists have proposed resolutions. Some suggest information escapes through subtle correlations in Hawking radiation. Others argue it is preserved holographically on the horizon itself. Still others believe our understanding of space-time requires revision before the contradiction can disappear. Despite remarkable progress, no experimentally confirmed resolution has settled the question. The paradox remains valuable because it exposes a deeper truth. knowledge is constrained not only by intelligence, it is constrained by where information is allowed to exist. Even if every law of nature were perfectly understood, observers would still confront barriers created by causal structure. This pattern repeats throughout modern cosmology. The earliest moments after the Big Bang remain partly hidden because the universe was initially opaque to light. Electromagnetic radiation cannot carry direct images from times before the release of the cosmic's microwave background, roughly 380,000 years after the beginning of cosmic expansion. Scientists investigate earlier epochs through indirect evidence instead. Gravitational waves may eventually provide additional clues. Relic neutrinos may preserve information from even earlier times. Yet, every proposed observational window carries its own physical limitations, technological challenges, and theoretical uncertainties. The farther we push toward the beginning, the more nature replaces direct observation with inference. That does not weaken science. Inference, built from multiple independent of evidence, has repeatedly transformed cosmology into one of the most successful quantitative sciences. But inference is different from complete access. The distinction matters because it separates confidence from certainty. The universe may consistently reveal enough information to construct extraordinarily accurate models while withholding complete verification forever. In everyday life, that difference feels negligible. In fundamental physics, it changes everything. A map can become increasingly precise without ever containing every feature of the territory. A theory can become increasingly successful without exhausting reality. For centuries, ignorance looked like a temporary condition waiting for better tools. Now another possibility begins to emerge. Perhaps some missing knowledge does not belong to the future. Perhaps it belongs to the architecture of the universe itself. The boundary is no longer defined by human capability. It is written into the pathways along which information is permitted to travel. And if information itself has borders, then every civilization, regardless of how advanced it becomes, may eventually discover the same unsettling truth. The universe is not only difficult to understand, parts of it may remain forever beyond the reach of observation, not because they are hidden, but because reality never intended them to be seen from where we exist. By this point, the picture has become difficult to ignore. Logic imposes limits. Computation imposes limits. Observation imposes limits. Yet, one possibility still seems untouched. Perhaps enough intelligence could overcome them all. If a civilization survived for millions or even billions of years, spreading across thousands of star systems and building computers beyond anything we can imagine today, wouldn't those barriers eventually become irrelevant? The idea appears throughout science fiction. Civilizations mature into entities capable of predicting galaxies, engineering stars, or simulating entire universes. Intelligence becomes something that grows without meaningful constraint. Physics tells a more restrained story. Every act of thinking is a physical process. A calculation is not an abstract event floating outside reality. It requires energy. It generates heat. It occupies memory. It unfolds over time. Even the most sophisticated artificial intelligence imaginable must ultimately manipulate physical systems governed by thermodynamics. That observation seems almost trivial until one asks a simple question. How much computation can the universe itself perform? Several physicists have attempted to estimate this by combining information theory with cosmology. While the exact figures depend on assumptions about the observable universe and its contents, the broader conclusion remains remarkably stable. The universe contains a finite amount of usable energy. It contains a finite amount of matter. It has existed for a finite amount of time. Those facts place an upper limit on the total amount of information processing that can ever occur within the observable universe. The limit is unimaginably large. It is not infinite. That distinction matters more than the number itself. Infinity is forgiving. Finite systems are not. Suppose a problem requires more computational steps than every particle in the observable universe could collectively perform before the last usable sources of energy disappear. From a mathematical perspective, the solution may still exist. From a physical perspective, it has become unreachable. The universe simply runs out of opportunities to compute. This idea forces an uncomfortable revision to the popular image of scientific progress. Progress is often imagined as an open staircase. Each generation climbs another step. Each discovery reveals the next. Eventually, every door opens. Physical limits suggest something different. The staircase may continue for an extraordinarily long distance. But some doors remain locked because the building itself was designed that way. Black holes offer one of the clearest examples. Jacob Bekenstein proposed that information storage is not unlimited. The amount of information that can exist within a bounded region depends not on its volume, as intuition might suggest, but on the area surrounding it. Stephen Hawking's work on black hole thermodynamics strengthened the connection between gravity, entropy, and information. Together, these ideas transform black holes from purely gravitational objects into laboratories for understanding the relationship between information and spacetime. They also hinted at something deeply counterintuitive. Information is not free. Reality keeps accounts. Every additional bit has physical consequences. Memory requires structure. Structure requires energy. Energy obeys conservation laws. Even forgetting information carries a measurable thermodynamic cost, a relationship formalized through Landauer's principle. Erasing a single bit of information cannot occur without dissipating a minimum amount of energy as heat. That may sound insignificant. One bit seems almost meaningless. Scale the process to planetary computers operating continuously over astronomical timescales, and the principle becomes unavoidable. Knowledge is not merely collected. It must be paid for. Every civilization accumulates understanding by spending energy that can never be perfectly recovered. The universe charges an entropy tax on learning. This does not imply that science becomes futile. Quite the opposite. It explains why scientific knowledge has always advanced through careful trade-offs rather than unlimited accumulation. Every telescope represents concentrated resources. Every particle accelerator consumes enormous power. Every interstellar probe carries strict mass limitations. Every detector sacrifices one capability to improve another. Even hypothetical civilizations approaching the limits of engineering would continue making similar compromises. There is no evidence that intelligence escapes economics simply by becoming older. Instead, economics becomes cosmological. The constraints expand with the civilization. They never disappear. Now consider prediction itself. Imagine possessing perfect knowledge of every particle inside an enormously complex physical system. Would forecasting its future become straightforward? Surprisingly, no. Many systems display computational irreducibility, an idea associated most prominently with Stephen Wolfram. In such systems, no shortcut exists that predicts the final state more efficiently than allowing the system itself to evolve step by step. While researchers continue debating how broadly this principle applies across nature, it illustrates another possible limitation. Sometimes reality cannot be outrun. The fastest way to know tomorrow is to wait until tomorrow arrives. If that principle governs even a fraction of natural phenomena, then intelligence encounters another boundary. Not one imposed by ignorance, one imposed by the structure of computation itself. The future refuses acceleration. This realization changes how we imagine advanced civilizations. Perhaps they do not spend their existence answering every remaining question. Perhaps much of their effort goes toward identifying which questions deserve asking at all. Knowing the limits becomes as valuable as extending them. That shift may represent a higher form of scientific maturity. The earliest stages of civilization chase certainty. Later stages learn precision. the most advanced stage may learn restraint. Not because curiosity weakens, because experience reveals that reality is selective about the answers it permits, and that possibility raises an unsettling thought. If every sufficiently advanced civilization eventually discovers the same permanent boundaries, then the greatest scientific achievement may never be complete understanding. It may be recognizing, with extraordinary confidence, exactly where understanding must end. At this stage, the investigation reaches an uncomfortable crossroads. If logic has limits, if computation has limits, if observation has limits, and if even advanced civilizations remain bound by finite physical resources, then one final question refuses to disappear. What does science become once it encounters questions that cannot be settled? For many people, that possibility sounds like defeat. Science has often been portrayed as a relentless march towards certainty. Every generation replaces myths with measurements, speculation with evidence, confusion with understanding. It is tempting to imagine that this process continues until uncertainty finally disappears. History suggests something different. Each major scientific revolution has reduced one category of ignorance while exposing another that nobody had anticipated. Newton explained planetary motion with astonishing precision. His equations worked so well that many believed physics was nearly complete. Then, light refused to obey the same picture. Einstein rebuilt space and time themselves. For a moment, the foundations again appeared secure. Then, quantum mechanics revealed a microscopic world upgraded by principles unlike anything classical intuition had prepared us for. Quantum theory became one of the most successful scientific frameworks ever developed. Its predictions have survived countless experiments with extraordinary accuracy. Yet nearly a century after its creation, physicists still disagree about what the mathematics ultimately says about reality. The equations work. Their meaning remains debated. That distinction is revealing. Scientific success and philosophical completeness are not the same achievement. The pattern appears elsewhere. Dark matter has never been observed directly, yet multiple independent observations strongly indicate that visible matter alone cannot explain the gravitational behavior of galaxies and galaxy clusters. Dark energy remains even more elusive. It is introduced to explain the observed acceleration of cosmic expansion, but its physical nature remains unknown. These are not small corrections added to an otherwise complete picture. Together, they dominate the energy budget of the standard cosmological model. In other words, the universe currently appears to consist mostly of components whose underlying nature is still uncertain. That fact is sometimes misunderstood as evidence that modern physics is collapsing. It is almost the opposite. The equations predict countless observations with remarkable precision. The remaining uncertainties stand out precisely because everything else works so well. The better the map becomes, the easier to notice the places where it still fails. This gradual refinement changes the emotional character of science. The greatest discoveries are no longer simply answers. Often, they are better questions. The detection of gravitational waves did not close a chapter. It opened an entirely new way of observing the universe. The discovery of thousands of exoplanets did not answer whether life exists elsewhere. It transformed that question from speculation into measurable science. The James Webb Space Telescope has not overturned cosmology. Instead, it has provided observations that continue to test how confidently existing models describe the earliest galaxies. Again and again, progress expands the frontier instead of eliminating it. That frontier may itself be permanent. Suppose humanity survives for another 1,000,000 years. Our descendants could possess technology almost unimaginable today. They may construct detectors spanning planetary or even stellar scales. They may manipulate matter with extraordinary precision. Artificial intelligence may assist every stage of discovery, yet every experiment they perform would still take place inside the same universe, the same speed of light, the same thermodynamic constraints, the same causal structure, the same mathematical foundations, the same finite resources. Their questions would become deeper. Their limitations would become clearer. There is an unexpected optimism hidden inside this conclusion. Science has never depended on possessing every answer. Its strength comes from distinguishing reliable knowledge from attractive speculation. Knowing where confidence ends is not a weakness. It is one of the discipline's defining achievements. This is why the most careful researchers rarely speak in absolutes. Confidence intervals replace certainty. Independent confirmation replaces isolated claims. Competing hypotheses remain alive until evidence separates them. The public sometimes mistakes this caution for indecision. In reality, it is an acknowledgement that nature is under no obligation to satisfy our expectations. Perhaps the deepest lesson of science is not that the universe is understandable. It is that the universe is understandable to a remarkable degree, despite imposing boundaries that cannot simply be wished away. The existence of limits does not diminish discovery. It gives discovery its value. If every answer were guaranteed, curiosity would become little more than a scheduling problem. Instead, every genuine breakthrough occurs against the possibility that the universe may refuse. That refusal is not hostile. It is indifferent. And indifference creates a different kind of existential pressure. Humanity is not engaged in a race toward complete knowledge. Humanity is participating in an investigation whose final scope remains unknown. The closer we approach the deepest foundations of reality, the more often we encounter an unexpected response. Not silence, not contradiction. A boundary, and every boundary carries the same quiet implication. Some mysteries survive not because intelligence is too small, but because the universe itself may be larger than any explanation it allows from within. There is a temptation to treat every limit we have explored as temporary. History encourages that instinct. Again and again, humanity has mistaken today's possibility for tomorrow's engineering problem. Continents once seemed unreachable. Atoms appeared indivisible. Other galaxies were thought to be small clouds inside our own. Every generation inherits boundaries that eventually collapse. That history makes optimism feel rational. It also makes one particular possibility difficult to accept. Some boundaries do not resemble the ones we have crossed before. They do not move as technology improves. They define the space within which technology itself must exist. Imagine a civilization so advanced that its achievements would seem supernatural to us. It harvests the energy of stars. It engineers planets. It builds quantum computers beyond anything we can presently describe. It survives for hundreds of millions of years. It maps every accessible galaxy, studies every stable particle, and constructs theories that unify forces we have only begun to understand. From our perspective, such a civilization would appear almost omniscient. From its own perspective, it might still be confronting unanswered questions, not because it lacks intelligence, because intelligence never escapes the universe that created it. It remains inside the same causal structure, the same thermodynamic accounting, the same computational constraints, the same information horizons, the same finite history. Perhaps the most profound realization available to any civilizations is not the discovery of another physical law. It is the realization that complete knowledge was never physically possible. That idea changes how we interpret one of humanity's oldest ambitions. For centuries, philosophers and scientists searched for certainty. The hope was that beneath every complicated phenomenon lay a simpler explanation, and beneath every explanation another, until eventually the chain reached bedrock. Modern science has achieved something extraordinary. It has revealed much of that underlying structure: the periodic table, general relativity, quantum field theory, the standard model of particle physics, cosmic evolution, nuclear synthesis. the expansion of the universe. Each represents one of the greatest intellectual accomplishments in our history. Yet none of them closes the investigation. Instead, each one exposes another layer where certainty becomes more difficult. A complete map of physical law does not automatically produce complete understanding. Knowing every rule of chess does not tell you how every possible game will unfold. Knowing the equations governing Earth's atmosphere does not permit perfect long-term weather forecasts. Knowing the equations of quantum mechanics does not settle every interpretation of quantum reality. Knowing the laws governing space-time does not reveal what lies forever beyond the cosmological horizon. Reality continues to separate description from total comprehension. Perhaps that separation is permanent. There is another consequence that rarely receives attention. If every sufficiently advanced civilization eventually discovers these same limits, then their scientific histories may begin to converge. Different species would ask different questions, develop different mathematics, invent different technologies. Yet eventually they could encounter the same frontiers, the same undecidable problems, the same computational ceilings, the same unreachable regions of space-time, the same recognition that some answers remain inaccessible regardless of who asks. In that sense, limitation itself may be one of the few truly universal experiences. Not language, not biology, not culture, constraint. For a channel called Cosmic Dread, it would be easy to end here by declaring that humanity is insignificant or trapped inside an unknowable universe. The evidence does not require either conclusion. Instead, it suggests something quieter. The success of science has never come from eliminating mystery. It has come from learning which mysteries yield to evidence and which ones redefine the meaning of evidence itself. Every generation inherits a frontier. Every generation pushes it outward, and every expansion reveals another horizon beyond it. That is not failure. It is the structure of discovery. The uncomfortable thought is that the horizon may never disappear, not because we are too early in history, but because horizons are part of the architecture of reality. If that is true, then the greatest misconception in the history of intelligence may be the belief that enough knowledge eventually becomes complete knowledge. Perhaps completeness was never the destination. Perhaps it was an illusion created by standing too far from the edge. Today, humanity remains only a short distance into its scientific story. We have listened to the universe for barely more than a century, with instruments capable of detecting its faintest signals. We have observed only a tiny fraction of cosmic history with any precision. We continue refining theories that future generations will almost certainly improve. There is every reason to believe our understanding will grow dramatically. There is no reason to believe growth and completeness are the same thing. The oldest dream of science has never been to collect facts. It has been to understand reality itself. The deeper our investigation reaches, the more that dream transforms. The final question may not be whether the universe has secrets. Every successful observation suggests that it does. The final question is whether a universe can ever become fully known by minds that exist entirely within it. If the answer is no, then somewhere beyond every future telescope, beyond every equation yet to be written, beyond every civilization that will ever exist, there will always remain one more question whose answer belongs only to the universe itself.